Hey everybody, happy Thursday. You are almost there to the end of the week here. Um, so you should have had your quiz already um, over optimization and 45 minutes, 50 minutes to finish up chapter 3, finish up kind of our last application of derivatives. Um, we won't be leaving derivatives behind. We'll be continuing on with other kind of things that come back to derivatives. But this is going to be our last sort of specific application of derivatives. And to understand, so the section that we're going over is section 3.9, differentials. It's also sometimes called linearization, which is kind of a weird word, but you'll understand where that comes from in a second. And the idea has to do, it goes back to that concept that I was talking a little bit about yesterday. How does your calculator actually calculate? So in other words, if I have my calculator, here I have my calculator on my phone, and I were to put in sine of 1.34, what would the calculator spit out and how did it come up with that number? Does it have all these values memorized? That would be a lot of different values. It does not have all those memorized. It actually does a calculation. To understand that calculation, we're going to figure out sort of a basic understanding of that calculation today. And then in order to understand kind of the full how does calculation actually work, you have to take a calculus course beyond this one. So we won't end up fully answering that question in this course, but there is an answer to it in like a next calculus course that you take. It involves something called infinite series, and we're not going to go through infinite series here in this class. It's just the we're able to do. We will today come up with kind of a simple answer for how those calculations work. So let me give you an example. Well, so the overall concept is that number into a general function like sine or tangent or other things like that is really hard. How do you plug 1.34 into sine? But if instead of plugging it into a function generally, you were able to plug into a line, lines are actually much easier to plug into. Like lines are generally in the form mx plus b. So if I'm plugging into a line, I'm just multiplying by a number and then adding a number. That's not usually that hard, other than instead of like taking the sine or cube root or tangent or secant squared or whatever. So the idea is if we can take our function and turn it into a line and plug into the line instead of the function, we should get as long as the line's close to the function, we should get a number that's close. And we can find lines that are close to functions when we use tangent lines. So let's just take as an example, I want to kind of give you an example here. We'll talk a little bit about that example and then we'll generalize it. So let's take the function sine. Okay. Now sine is definitely not a line. But if we were to zero in on a particular part of sine, in this case, let's zero in at x equals 0, and we were to look at that a little bit more, sort of blow that up, that would actually look a lot more like a line than, say, the original function does, okay? So what this means is that if I wanted to plug a number in that's really close to 0, plugging it into the tangent line versus plugging it into the function, they're basically really close. Now, I can't do that with functions that are with numbers that are really big, but for numbers that are really small, that would work. So for instance, so let's figure out, first of all, what is this tangent line? In order to do that, in order to figure out the equation of any tangent line, I need a point, which in this case is 0, 0, and a slope. Now the slope comes from the derivative. The derivative of sine is cosine, and the derivative at 0 is the cosine of 0, which is 1. So that's my. So I have a point of 0, 0 and a slope of 1. So the tangent line that I'm interested in here is the equation, the point slope form for any equation of a line is y minus y1 times x minus x1. So in my case, my y in my point is 0, my slope is 1, and my x in my point is also 0. So the equation of the tangent line here is y equals x. And what that means is when x is very small, so if x is close to 0, in other words, it's very small, plugging into sine is basically the same thing as plugging into the tangent line. Okay, and in this case, the tangent line is just x. So if I were to, for instance, wanted to take the sine of 0.02, this close to 0, so you can just use the tangent line. The tangent line would say that you just get 0.02. Take a second on your calculator and just calculate the sine of 0.02. And make sure you're in radians. When I do that here, what I get is 0.0198, 199986. See how close those are? That means that that tangent line is a really good approximation to the function values. Instead of plugging in the function, I can plug in the tangent line. That's actually what your calculator does. It kind of plugs into a line. It does something else. But if we use lines instead of the original functions, that actually makes our life easier. The other thing that's really interesting to think about here, do you remember when we did this limit as x goes to 0 of sine of x over x? We actually use the squeeze theorem here to end up getting this to be 1. But one thing I want you to think about is when x gets close to 0, the sine function is basically its tangent line, which is x. But x over x is 1, and that kind of explains why that limit would be 1 the way that it is. So there are a lot of things that really give some interesting insight into the functions when we look at their tangent lines. Okay? Now turning a function into its tangent line, turning a function into a line, that's called linearization, which is a weird word, but it's turning something into a line. And the idea is lines are a whole lot easier to plug into than original functions. So if you give me a function and want a value, what I do is I find a line that I can plug into easily, and I plug into the line instead of plugging into the function. So that's the concept behind what we're going to do here today. Okay? So let's look. Let me give you another kind of example problem here. Okay, I want to approximate the square root of 3.9. Okay? Square root of 3.9. Now, the thing that you need to think about here is what function are we dealing with, and what point are we plugging in, and what point is nice to plug into that function that's nearby. So in other words, for instance here, if I wanted you to calculate the sine of 0.02, well, the sine of 0 is an easy place to calculate. So if we found a tangent line at 0 and plugged 0.02 into the tangent line instead of plugging 0.02 into the sine function, that makes my life a lot easier. So in a similar way, for this approximation, if I take the function square root of x and I look at what's going on at x equals 4, 4 is an easy number to plug into the square root of x. Okay, let's draw this function. 1, 2, 3, 4. Okay. At 4, if I plug 4 into the function, that's a nice number, right? Plugging in 4, I get 2. That's a very easy number to plug in. What I'm going to do is I'm going to find the linearization at 4. I'm going to find the tangent line at 4, and then I'm going to use the tangent line to plug in 3.9 instead of using the function to plug in. Because I don't know how to take the square root of 3.9, but I can plug 3.9 into a line. That's not a problem. Does that make sense? Okay. So let's find the tangent line. So for the tangent line at x equals 4, first I need a point. Now my point is 4 comma what I get when I plug 4 into the function. So that's 4 comma 2. And then I need a slope. So to get the slope, well, the slope everywhere is the derivative. So I'm going to have 1/2 x to the minus 1/2. Okay. Which, if I clean that up a little bit, so the slope everywhere is 1/2 square root of x. I don't want the slope everywhere. I want the slope at 4. That's going to give me my slope of this tangent line. So the slope at 4 is 1/2 root 4. That's root 4 is 2. So 1/2 times 2 is 1/4. Okay. So my tangent line is going to be y1, 2 equals slope times x minus x1, 4. That's going to give me my tangent line here. Okay. So in other words, y equals 2 plus 1/4 x minus 1/4 times 4 is 1. Okay. Make sense? So now what I'm going to do is instead of plugging 0.39 into the square root function, which is really hard for me, I'm going to plug it into my tangent line at 4, which is much easier. Okay, so instead of plugging into the function, I'm going to plug into the tangent line. So I'm going to take 2 plus 1/4 of 3.9 minus 1 and see what I get here. All right, now I could divide 3.9 in my head. I'm going to kind of be lazy here. Okay, so 3.9 divided by 4. Okay, plus 2 minus 1 is, and I get 1.975 here. Now I want you to take a second and just do the square root of 3.9 and see what you get. If you actually did this in your calculator, what you find is 1.97484. You see how close those are? Those are really close. In other words, using the tangent line to approximate the square root function gave me a really good approximation to that number. Now, it wasn't perfect, but that's not what I'm looking for. I'm looking for a really, really good approximation. Okay? Does that make sense? So let's do one more. Let's do one more example here. Okay. Okay. So again, the idea, linearization means tangent line. It means find the tangent line somewhere nice and use that to find values for the function. So let's do one more example here. Let's approximate 1/4.01. Okay? All right. So 1/4.01. So let's first identify what function are we dealing with. It looks like the function we're dealing with is like 1/x. And then we're looking at x equals 4. Okay? So, 1, 2, 3, 4. Here's the function 1/x. I would expect this number is about 1/4. It's going to be about 0.25, but I think we can do better. Okay. That's 1 at 1. So it's 1/x. There's some other part over here. So what we're going to do at 4, which is a number close to 4.01, we're going to find the linearization of 1 over x. We're going to find the tangent line. And then instead of plugging 4.0 into 1 over x, we're going to plug that into the tangent line and see what kind of approximation we get. Okay? So let's give that a try. So let's find the tangent line. So now the tangent line at x equals 4, this tangent line here, first we need a point, so it's going to be 4 comma what we get when we plug 4 into the function, 1/4. In other words, 4 comma 0.25. And then this is x to the minus 1, so the slope everywhere is going to be minus x to the minus 2. In other words, negative 1 over x squared. Now the slope at 4, which is what the slope at 4 is negative 1/16. And so my equation of my tangent line, my linearization, my equation line is y minus y1 equals slope times x minus x1. So in other words, my tangent line equation is y equals 1/4 minus 1/16 times x minus 4. That is my tangent line equation. Okay, and now what I'm going to do is instead of plugging 4.01 into this 1 over x function, which I don't know how to do, I'm going to plug it into the tangent line at 4. So I have 1/4 minus 1/16 times 4.01 minus 4. In other words, I'm going to have 1/4 minus 1/16 times 4.01 minus 4 is 0.01. Okay. So I'm going to take 0.25 minus 1/16 is 0.0625. Okay, we could do this in a calculator. So multiplying by 0.01 gives us 2 extra zeros. And then if we subtract now, so we have all right, we get 249,375. Okay, that's our approximation. Now, I want you to notice if you actually take 1 divided by 4.01, the actual answer is 0.2493765. Notice that our answer is right to 5 digits and really close at the 6th digit. So that's a really good approximation. That tangent line is a really good approximation. And one other thing that I want you to see is that since our tangent line is under the actual function, plug into the tangent line, the number we get is going to be a little smaller because the tangent is under the actual number we would get if we plugged into the function. So in other words, this is going to be an under approximation because the tangent line that we're using is under the function. If the tangent line was over, like it is over here, what we get is an over approximation. Make sense? So that concept of linearization actually allows us to approximate numbers, and you're going to see on your homework several examples where they ask you, number one, they ask you to find the linear approximation. That means the tangent line, the linearization. They're also going to ask you to use differentials or use tangent lines to approximate the value of a particular expression, right? Now, there's one other way that this idea of tangent line is actually really, really useful. So let And this is where the word differential will come in because we have talked about that. Okay. So here's the idea. Sorry, my screen went dark here. Hold on 1 second. There we go. Okay. So the other way that we can use tangent lines, the idea here actually has to do with measurements in science. So if I have some function, okay, so y is a function of x. Here's y, here's x. And I measure, like if I'm measuring a radius, and I measure the radius to be 10 centimeters, and then I'm going to use the radius to calculate something else. So I've got like an area. Area is pi r squared. So if I measure the radius, I can use that to calculate the area. So if you had a plate and you wanted to measure the radius of the plate, you get the area of the plate. Now, the problem with measurements in science is that our measurements are not always accurate. And that inaccuracy, being off a little bit in one thing, when you take that number and then use it to calculate something else, that error does something called propagating. It shows up or blows up. It can get bigger or smaller depending on how you're taking that number and using it. So the question is, if you have error in one thing that you're measuring and then you use it to calculate something else, how does that error show up over here? The way that we're going to answer that, that's actually a fairly complicated question, but if you use derivatives, you can find a very simple answer to that. So the idea is that if I have some function, like imagine if this was, for instance, and then area, it would be pi r squared, so we'd have some curve here. If this x value, we're going to kind of draw this in two different ways. If this x value has a little bit of error, we call that error delta x. Let me write it a little bigger so you can see it. Delta x, the Greek letter delta, it's actually capital D in Greek, delta, usually denotes change in something, okay? I'm trying to draw something that's really similar. Not quite getting it here. Let's try this again. Okay, so the question is, if my radius, for instance, was off by a little bit, like if I measured it to be 10 inches and it was off by maybe possibly by half an inch, half an inch would be my delta x. X would be 10 inches. So this is my calculation. This is how far I'm off. But if I'm off, then the y value is also off, right? The actual y value is off by some amount that we're going to call delta y. So if my x value moves, my y value is going to be off by something as well, and I want to know how much that is. But typically the way that you would have to calculate that is if it was like 10, and then this distance was 0.5, then I would have to plug in 10.5 into the function. Then I'd have to plug 10 into the function. And then I'd have to subtract those two, and then that's going to give me how far off those two things are. That's really annoying. We don't want to do that. We want to figure out an easier way, okay? So the easier way, turns out, is by using derivatives. So instead of using the function, we're going to use the tangent line. In other words, we're going to use the slope. And we're going to call the same distance delta x, I'm going to call it dx, okay? There's a suspicious reason that I'm calling it dx. Don't worry about that right now. If instead of using the function, I'm going to use the tangent line has a slope that's the derivative at this point. And that derivative we also tend to call dy dx. part of the reason that Leibniz came up with this notation is rise over run. If dx is a small run, then dy is a small rise, and dy over dx gives me the slope there, which is the derivative, okay? So here's the idea. Instead of plugging into the function, which would be here, we're going to plug into the tangent line, and we're going to get how far off y is using the derivative instead of using the actual function. Now, the way that we do this is I'm going to take this dx is now a length, and I'm going to move it to the other side, and I'm going to get an equation that says dy is the derivative times dx. Okay, and these things right here, this dy and this dx, are called differentials. Now, this is kind of an abusive notation. You're not supposed to take dy over dx that's a derivative and kind of think of it as a fraction that you can move around. But it turns out that in many cases that works okay. You can actually do it. So we're going to call these differentials, and the idea is if x is off by some amount, then the way that I figure out how y is I take that amount that x is off and I multiply by the derivative. And that gives me an approximation to how far off y is. Okay? So what we're going to do is we're going to just do a couple of examples of this, just to kind of, we'll do one general example and then two very specific examples. All right? How much room do I have here? Let me scoot this over just a little bit. And we'll do an example over here. Okay, so let's first start with a general function. Let's take the function y equals x squared at x equals 10. And let's assume that our error is 0.1. Okay, so my delta x is 0.1. And I want to know how far off will y be if I have an error of 0.1 in x, how much error am I getting in y? Now I could do that by figuring out what is y when x is 10, then what is y when x is 10.1, and then trying to subtract the two to get how far off the y values are. I'm not going to do that. Okay, what I'm going to do instead is use differentials. So differentials tell me dy dx is the derivative. So in other words, how far off y is, dy, is the derivative times dx. Now in this case, the derivative is 2x. So how far off y is about 2 times x is 10 here, times the error, and the error here is 0.1. So in other words, 20 times 0.1 is 2. So if I have an error of 0.1 and a value of 10, and then I use those in a function, that function is going to have an error of 2. That point ended up getting a lot bigger. It ended up becoming 2. Does that make sense? Now the y value at 10 would be 100. But the error there would be 2. So whereas we had 1% error here, we ended up with 2% error, the y value. So let's look at this in a couple of contexts where that might actually show up in a science class somewhere. Like how would this actually show up if Mr. Nemec was talking to you, or if we were doing physics or chemistry. So let's take a couple of simple examples. We're not going to get overly complicated here. But if we take a couple of simple examples, the first example, let's suppose that we're measuring the area of a square piece of paper. Okay. Okay, so I'm going to call the side S. And we're going to measure S, and we end up measuring S, and S ends up being 8 inches, but my possible error, which I'm going to call delta S, is about 0.1 inches. Okay. The question is, now if I use this to calculate an area, how much error is going to show up in my area, potentially? My error in the side is 0.1. So if I had my ruler up, I can tell up to about 0.1 what the measurement is, but I can't get beyond that. So if I use that potential error, how does that show up when I use this number to calculate? So area is side squared, and so the differential dA is the derivative times ds. Now the derivative is, s squared is 2s, so what we're looking at here, 2 times 8, and my error here is 0.1, so in other words, 16 times 0.1 is 1.6, so my error in my area calculated it using 8, I'd get 64 inches squared. But I'm potentially off, my error in my area is off by at most 1.6 inches squared. So it could actually be 66 inches squared, it could actually be 62 inches squared based on this difference in my side. Does that make sense? Let's do one more. Let's suppose that we were measuring a basketball. Okay, and we want the volume of a basketball. Okay, and let's suppose that we could actually measure the radius. So let's suppose that we measure the radius to be, let's say the radius is 1.2 feet, but the error in the radius is about 0.05 feet. And then the question is, what kind of error am I looking at with the volume? Okay. Now, you actually wouldn't, just as a side note, you wouldn't, if you were measuring a basketball volume, you would probably not measure the radius, you'd measure the circumference. You'd use the circumference to find the radius, and then you use the radius to find the volume. So there would be a couple of different calculations that would happen here. For now, we're making it simpler. We're just looking at the radius. But my volume formula, do you remember a volume of a sphere? Okay. Volume of a sphere is 4/3 pi r cubed. Okay, so my error in my volume is going to be the derivative of this times my error in my radius. So the error in the volume is going to be, the derivative of this is 4/3 pi, and the derivative of r cubed is 3r squared. So now 3's cancel. The error in the volume is going to be 4 pi times my radius, 1.2 squared, times my error there. Okay, so if I were to calculate this, (1.2) times 1.2 times 0.05 times 4 times pi gives me 0.90, about 0.905, so about 0.9 the feet of error in my volume, given what's going on in the radius. Now the volume, if I were to actually calculate this using 1.2, 4/3 pi r cubed, let's just calculate that real quick too. Times, okay, so this actually is 7.24 cubic feet. I want you to notice that even though the error here looks small compared to the radius, the error with the volume is about 1 cubic foot versus 7 cubic feet. So the error actually gets bigger as we do that, and you can use this to calculate a percent error. We're not going to do that here. You're going to study that in science class. But this is one way to figure out how error in one situation is going to then propagate into error in another situation. So that's another nice differentials. Yeah, so we're not going to look at too many other application derivatives right now. When we go into next week, we're going to look at we're actually going to look at reversing the process of differentiation, which is called anti-differentiation. So we're going to do that briefly, and then we're going to take a totally new concept that doesn't seem like it's related to the previous stuff about area, and we're going to actually find out that it is related to the previous stuff, and it's related in a pretty shocking way. So we'll start that next week. Everybody have a great weekend. You might have a little bit more time here to work on any homework questions that you have. Yeah, so God bless, and I will see you on Monday.